What's the question?
Okay. Hello and welcome to lecture 17 of Rob 101. Unlike what you expect, today is about nonlinear equations. You did not sign up for nonlinear algebra, but we're going to start a somewhat non-traditional journey of solving nonlinear equations, and maybe next lecture and in the future lecture, you see how they can get connected to linear algebra and how we use linear algebra to numerically solve problems that are nonlinear. And we do not have a formula or closed form way of solving them in general. And in particular, we're going to talk about two algorithms for root finding. So our objectives are to expand your horizon a little bit beyond linear equations, because it's important, ultimately it's important you be able to connect your problem to what you learned here and how to solve your problem. The problem that you will face in reality, they might not come in the form of a system of linear equations. Nobody's going to hand it to you like that. But you can see the process that how the problem can be converted. And as part of the solution, we often need to solve a system of linear equations as part of an algorithm. Another important concept that comes later in linear algebra books usually is the idea of iteration. Coming up with some succession rule or some process that we can calculate some results and next time use the previous result for updating our solution. And then we continue this until some sort of convergence. That idea is called iteration, and algorithms that work like that are called iterative algorithms. So we construct an algorithm that iteratively solves the problem, and we will see today it is approximate, but we have control over the accuracy usually, and we reach a small number that is probably good enough for us to accept it as a solution. And we are going to do that without assuming you know calculus. You might know some, or you might not be familiar with calculus. We do not intend to use calculus knowledge, although we point out what you will see in a calculus course, and it might make it more interesting for you at the time when you look at it because you have an application in mind for the topics already. So we want to talk about root finding. What does it mean to talk about a root of a function or an equation? And we want to come up with algorithms for solving that. One of them is bisection method. It is quite intuitive and simple. And the other one is Newton's method. Now, we also need to talk about the notion of slope and linear approximation of a function. So these topics will come up, and we try to explore these ideas within these algorithms. So first, let's talk about root of an equation. You're probably familiar with a quadratic equation, and you learned that you can calculate the discriminant delta and then say that when it's negative, the roots are, there's no real roots. You might have known that are complex rules. And if it's positive, you can find two rules, and you have an equations for that. You don't need to write code. You don't need to do something complicated. But in general, this is not true. If it's the polynomial that you want to solve, is above degree of 4, then we don't have a formula for that. So that's a problem. But we also might face any nonlinear function. It might not be a polynomial. So then the question is for an arbitrary function, not necessarily polynomial or cases that it's possible to find a solution. Let's leave those special cases out. For a general nonlinear function, nonlinear because now we have squared. We might have sine, cosine, exponential. It is not just a linear combination of coefficients and variables. For a general nonlinear function, we want to find a way to talk about its root. And we're going to limit ourselves to the cases when we are after real number. The algorithm is trying to find a real number. Might seem a little limiting, but in fact, a lot of problems we solve in science and engineering fall into that category. So it's part of the math, but in application-wise, it covers a wide range of problems. And if you want to start a more broader exploration, it starts with real numbers anyway. We have to extend it to complex numbers once we understand the real case. So what do I mean when I say a root of f of x equals 0? First of all, we need to talk about the notion of function, a map, a rule that takes an input from some domain and then map it to a range. To be a function for every element of the domain, the function should map that to only a single value in the range. So it is not a map that takes a value in the domain and map it to multiple points in the range. That's not a function. We're going to see an example of that. So then we have a function, and for example, our familiar matrix equation, that was a function. X could be in Rn, but f could be in Rm in that case. Today, we're going to talk about simpler functions. This A can be a row vector, for example. Maps to just a real number, okay? And then next time, we will extend it to vector-valued nonlinear functions. So let's define an equation, f of x equals 0. Then you ask, what are the values of x in the domain that satisfies this equation? So any value of x, such as x star, in the domain that satisfies this equation, it's called a root of f of x, a root of this function. So it is possible to have multiple real solutions or no solutions, just like quadratic equations. So nonlinear functions are unlike linear functions because we spend a lot of time talking about if there is a solution, if we have these conditions, right? If the right-hand side is in the range of the matrix and all of that, there is a solution and that's unique. That's really nice. You don't have that for nonlinear functions. You might have multiple solutions, and it's not always possible to find all of them. Your search may be local. You might find one of them. So it's very difficult to talk about a global perspective of nonlinear functions. Now, what about, let's just to clarify, when you see different models of writing, what about this function that the right-hand side is not 0, it's pi? Technically, it's not the same problem, but it's not a problem for us because we can just define a new function, f bar, which is f of x minus pi, and then we attempt to find a root of f bar. And then if you know that, then, well, f bar is f of x star minus pi equals 0. Then the root of basically f bar will satisfy this equation, right? So if you have something that is non-zero, you can just redefine your function and solve for that. Then x star is the root of f bar. So the terminology of the root goes to the function that satisfies this equation, right? X star is not a root of f of x. It's a root of f bar, if you want to be precise with your language. We need another notion that in a calculus course they will cover it in discussing details, take the limit, left, right, and all of that. Very informally. Your function takes a real number, gives you a real number. If you can hold your pen and never lift it, right, in the domain, that's a continuous function. If you have to lift it, that's not continuous, okay? Now, this condition, besides the condition that to be a function, it needs to map each value of the domain to a single value of the range, that's good enough for us. That's a continuous function. Then we can run the algorithm. Because the algorithms that we run, if you have this sort of gap, then it doesn't work. It breaks down, okay? So we are going to talk about continuous functions, and this informal definition is good enough for us to get results in practice. A course on analysis and calculus, they will, of course, formalize this and use epsilon delta and a lot of other definitions. Some examples. The first function here is continuous, because I can just start from here and draw it. This one is not, because I need to lift my pen and continue. What about the third one? An opportunity for you to chime in. What about the third one? I can continue without lifting my pen. Is this continuous? Luke says fails, vertical line test. Okay. Yes, it's not a function because of this vertical line means that it's taking a single point in the domain and then mapping it to multiple values in the range. That violates the condition for being a function, then regardless of being continuous or not, right? Now, you could obviously have a little slope here, then it's okay, right? But the extreme case, there's a vertical line, it's not okay. So the third one is also, this is not a function. So we can't talk about its continuity to begin at all. So this is just good enough for us to continue. There's a theorem in calculus. It has a name. It's called intermediate value theorem. It's a very intuitive theorem. It says that if your functions over an interval from A to B, if you take A and B and evaluate your function, f of A and f of B, and if you multiply them, if the sign is negative, then there is a real number between A and B, you can call it C, such that C is the root of your function. And you can say that the values of a and b to bracket the root c. Now, what this means, I'm not going to prove it, dive into the calculus or analysis to show it. You can just write a bunch of stuff and show like the sandwich theorem that from both sides they're reaching to the same point, and then must be basically from both sides your value of function converges to 0, and then that c must be the root, but very intuitive, graphical idea. Now to meet the condition that f of a times f of b is less than 0, what does it mean? That means one of them is negative, right? Because if both of them are negative, then, well, the product is positive. If both are positive, the product is positive. One of them is negative. Let's say here, right? Well, we have it in the picture. Here and B here. So we do need a 0 crossing line, right? To be negative on one side and positive, that means at some point the function needs to cross the line because the function is continuous. Then it's obvious that at least there is one point. The theorem doesn't tell us how many times it will cross, because you can have, just like this picture here, you can have 1, 2, and 3, because we are only aware of these two endpoints. So the theorem says that at least there is a c, that's going to be the root of the function. So graphically, you can just prove it like this for yourself, and again, that's good enough for us. We'll see how this condition helps to initialize our search, our algorithm. Okay, so this is called the intermediate value theorem. If f of, in an interval a and b, f of a times f of b is negative, then there is a root between a and b. So this was a brief introduction to some notions that we're going to use. We're going to switch to notebooks. Do you have any questions until now before I want to switch to notebooks or other type of slides, not PDF. No? No question from chat? Okay. Now, I have uploaded the notebooks. These are Julia notebooks. I'm going to run it locally, but you can run it locally or on IllumiDesk. If you cannot run notebook, you can open the HTML version. I also exported HTML slides from my notebooks. That's also a good way to just look at them. In fact, I might use the HTML slides first. Okay, so now we want to talk about algorithms that, given a function, right, it will find the root for us. It's an important problem on its own, but you might say, what's the point of it, or what is it good for in a linear algebra course? Well, it is good because later when we talk about vector valued functions, then we bring in some other concepts of calculus, but in a discrete sense that we talk about it today. Then the root finding will lead to algorithms for optimization. To find the root of a vector valued function, we start from here, then we end up solving a linear system of equations. And then later, we want to optimize a function, an objective function, then we end up with algorithms One of them is called gradient descent. Another one is called Newton's method. And the gradient descent is actually the algorithm people nowadays train a neural network with it. Not the vanilla version. There's been much research on it. There's a lot of variations of it. But the essence of it is that. It's the gradient descent that we cover here. That's just a search to find the best parameters for a neural network that can take an input and give you an output, approximate a map, a function for you. But that's a very complicated function. You have billions of parameters, right? But deep down, it's a gradient descent. But it starts from here, understanding these concepts. All right. The first and maybe a very intuitive, the most intuitive algorithm to find a root. It's called bisection method. So this is a root finding method that you can take a continuous function and repeatedly you can divide your search interval to half and then under some conditions continue the search. And then by splitting your interval to half each time, you're making that interval that we talked about in intermediate value theorem smaller and smaller until you can just trap the root in a very, very tiny interval, and that's your solution. So generally, that's the idea. So I have a function f of x. I start from interval a and b. Now I know that f of a1 here, and f of b1 times f of a1 times f of b1 is negative, right? So the idea of bisection method is that, well, the first step, let's say k equals 1, or n equals 1. This is my interval. Then I'm going to split this interval to the second one, right? Then I'm going to split it again and again. You keep doing that, right? You need a computer to do that. It's very tiring to do it by hand. You're going to hate it. After a few iterations, you never want to do it. You write a code, you keep doing this, and then the computer will find it. Now, how do you know which side, right? Each time I have two options. Should I pick the left half or the right half?
So is this side where f of a times f of b is less than 0?
Great. That's exactly what we do, Ben, is that check this condition. If it's true for that half, then pick it. You know there's a root there, right? The theorem is telling you that. So let's turn this into an algorithm. Yeah.
Is this assuming that there's only going to be one root in between, like, the result?
Good question. Is the algorithm assuming there is only one? We don't assume there is only one, but we are going to find one. Because the algorithm is not capable of tracking multiple roots if they're available, because this process is only going to narrow down to finding one root, right?
So if both of them, if both f of a or both sides of it result being less than 0, then it will choose, I guess, the first one it calculates?
Depend how you implement it, right? Maybe you just check the first one. If it's true, you just take it, right? Then you always go with the first one that is true. Which you can sense the limitation of these algorithms that you need to start somewhere, and that initialization actually affects your solution. That's the sense of local search, local algorithms. Okay, so let's talk about iteration tasks. So we want to take f and the interval a and b, and we can evaluate the function, right? We assume we know the function and we can evaluate it. So we have access to function evaluation, so we can get f of a and f of b, and we assume they have the sign of the product is negative. Then we know at least there is one zero crossing within that interval. Each iteration is like this. So for your algorithm, it's always good to write down what are the steps, right? If you can write it down, describe it, then it's concrete, then it's precise. Then you can turn it into maybe pseudocode, a little more closer to the programming language. Then maybe you can use one specific language to implement it. But the algorithmic implementation on the paper is very important because that's independent of the syntax. It means you understand the specific steps that we're going to follow. So first, we are going to calculate the midpoint, C. A plus B divided by 2. Then we evaluate the function at C. At this point, maybe C is already the root, right? So it sounds like we can check if we know the solution. If the convergence is satisfactory, then C minus A must be small, right? The absolute value of f of C must be small too. Then we can return C as the root, right? And stop iterating. So the algorithm usually takes something as input and gives you an output, and you need to be specific about that. Here we take the function a and b and give output C and f of C if you want as an optional output.
Should it be also like less than or equal to 0 to take into account if it just like touches the x-axis and back up?
Oh, we haven't done that. That's step 4. Step 3 is just checking that if it's converged or not.
Right, but I'm saying in general, like, there's like, what if it only, like, if the function just touches the x-axis and then doesn't go down but goes back up, like, that would still be a root, right? So when you
yes, because it is 0, right, at some point.
So isn't then not a case where f of a and f of b would still be greater than 0, potentially, but like it touches the x-axis and it just bounces back up?
You are talking about a very special case. So let me finish item 4 and then I'll give that example. So we check the convergence and then we check the sign of f of C, right? Then we want to replace A or B with C, one of them. One of them should be replaced, so we work with half interval, half of the interval. We check the sign, right? If f, let's say f of A times f of C is negative, then we pick that interval. And then we go all the way back to continue until convergence. That's the idea of iterations. Now, a question came up is, what if the function is, I think you have something like this in mind. There's only a single point. Now, the intermediate value theorem didn't tell us that if that's not true, there is no root, right? First of all. The theorem never said that. The theorem said, if that condition is satisfied, then there is at least a root, right? Maybe there are multiple roots, maybe the condition is violated, maybe there is a still root, right? It is true that for using bisection, we rely on that idea. And there is nothing negative here, so we cannot use that. although Newton's method find this root very quickly. This is like canonical example. It's a default example for Newton's method for finding roots, right? So that, right now, we're not using the notion of slope and derivative. Newton's method will use the notion of linear approximation in the slope. This is a default example for Newton's method, which is a very smart algorithm. So we're going to get back to this, right? So then this algorithm might not be suitable for this one, this model. Why? Because, well, the algorithm is telling us, give me f of a and b such that the signs are opposite, right? It's not designed for that. So in a sense, it's not fair to penalize something for something that's not designed to do. It has a very limited application, and it's clear what it is. Okay, so I need to clear my screen because this writing is independent of the slide, unfortunately. Okay, let's look into an example. Simple example, we can know the solution and see how the algorithm performs. The function we're looking at is f of x equals x minus 1 squared minus 4. We know that if you plug in 3, that's the root. So 3x equals 3 is the root of our function. How do you pick an interval? It's like a very useful information you need to get from somewhere. Now, these are one-dimensional functions you can easily visualize, right? I'm not visualizing here, but you can visualize your function, right? That's just a plot. Or you can just try. We already know that, let's say, f of 0 is minus 3, right? F of 5 is 16 minus 4. It's positive, it's negative. So that's good enough. This is the code I implemented. So so to turn those steps into algorithm, right, the structure of the code that you will implement probably will be similar, but it's not about having the exact line and what you have to be the same, right? As long as it's structurally correct and implements the same algorithm. So what am I doing here? I will also open the notebook. We can run it and change it. And you can change it yourself, too, if you have the notebook. So what I'm doing, first, I'm implementing my function. In Julia, it's very easy. Just say function f of x, right? And return x minus 1 squared minus 4. That's my function. I start with the interval a and b. So I give the algorithm, give a and b to my code. I need to set a convergence threshold. We'll see why. I call it delta here. You could call it anything else. My numerical 0 here is 1 times 10 to the power of minus 9. Is that correct? It's been a long time having converted e to this scientific way. So that's basically means 0, 0, 0, 0, 0, 0, 0, a lot of 0, 1, right? So that's my 0. That's good enough. I call that to be the root. Now you need to set a maximum iteration, because if you don't do that, in a lot of algorithms, you might get stuck. What if it never converges? You just stay there forever, right? So make sure you have a maximum iteration. For me, it's 100. I also want to count the number of iterations, because I want to know after how many iterations the algorithm converges. I call this n here. And you see I have a lot of comments, because a code without comment is a shameful code, because you won't remember yourself. If you come back after a few months or 6 months, you're not going to remember what you did, right? Just n equals 1 can be anything. So what's the difference between good comment and bad comment? Our fellow programmers.
I guess a good comment it's actually telling you what you're doing, as opposed to a bad comment just is giving you no information.
Almost, yeah. So a good comment is telling you why you're doing this and what you're doing, right, in that area. The bad comment is just getting stuck into the mechanics of, I'm going to multiply x and y, next line x times y. Like, that's useless, because you can already see that x being multiplied by y. But good comment is saying that multiplying these to get something that, for example, I don't know, compute the right-hand side of this famous equation, right? Something like that. So leave good comments in code, as opposed to redundancy, that you already see what's being calculated. So, and I'm not saying that assign 1 to n in a comment. I'm saying that this is counter for my iteration. Okay, so now you understand what is this variable for. We need a while. I'm using a while loop because that seems a natural way to do it. I'm going to iterate while n is less than maximum iteration. You could use 4 probably too, right? So while the number of iteration n is less than maximum iteration, while this condition is true, do whatever is inside the while. What was the first step of the algorithm? The first and second step. First step told us to calculate c, right? The second step told us evaluate f of c. Now I'm doing it in one line. You could separate it. So calculate c, which is a plus b divided by 2, and then evaluate f of c. Remember, my function is defined here, right? So I can call f of c in the code. Then the third step was that see if it's converged. So I am telling the code to check if the absolute value of f of fc, that is f of c evaluated, is less than my delta convergence threshold, or if the absolute value of c, the difference between c and a, is also less than that delta, then print converge and break. This break is very important because it breaks the loop. Otherwise, it will still continue. So break breaks a while loop, and then you come here. Whatever is here, you will run. Now, what does it mean c minus a being less than delta? If you can imagine that. Why not b minus c? What's so special about a? So it doesn't really matter, right? So C is supposed to be the midpoint of A and B. So whatever side you choose. Now, if the distance between A and C is really, really small, that means the interval is super small. That's already less than your threshold. So we better stop, because cutting the interval to half is beyond our numerical resolution that we're after. Okay, so there's no point to continue. And absolute value of f of c less than delta is obvious. That means the f of x equals 0 is almost satisfied numerically. So if that's not true, then it's not converged. Then if the condition is false, the algorithm will continue. Count 1 for the iteration, plus this means n equals n plus 1. It is extremely painful to code this. You have to do it in MATLAB, but in Julia, luckily, they added this. Now, the final stage of the algorithm. We need to update the interval because the search needs to continue. So if the sign of f of x, f of fc, which is f of c here, double equality sign to check if they're equal. If the sign of fc equals the sign of f of a, because then a is no good, right? If the sign of f of c and f of a are the same, then we can replace a with c here. If not, well, we can just replace b, because we know sign of f of c and f of a are the opposite, and that's good enough for us to continue, right? Now, this will continue until convergence. Here, we will run it again. We can change the threshold and see what happens. But with this setup, the algorithm converged after 33 iterations. This is a very trivial example. I doubt you have the patience to do this by hand, right? And it's a single variate. Nobody cares in 2021. But you will see how this structure will help you to implement multivariate functions and solve optimizations. So what's the actual value of C? C is 2.99999 continues, right? What was the true root for the 3? So C equals 3 was x equals 3 is the root. And that's not too bad, right? We have a lot of 9, and it's all because we set the threshold, right? The function needs to be smaller than 1e negative 10, negative 9, and it is. It's absolute value to be precise, because it is negative, but that doesn't matter. So this is bisection algorithm. I'd like to point out that this was also more than just an algorithm. This was a process of look at the theorem, see how you can use that to design an algorithm, write your steps or pseudocode, and then write a program and solve it. This is a very important thought process. It's used extensively in solving new problems. You can turn your knowledge into algorithms that will work. Given some regularity conditions, here is that, right, the functions have opposite signs and other things we talked about. So I want to move on from this slide, and let's look at another example. not so easy to guess the root by just looking at it. So what we're going to do, we're going to visualize the function because it's single variate. And there is a zero crossing here. Anything you find on the side should be fine, right? Let's pick 0 and 4. That's my choice here. And this is my function. Now tell me what lines are changed here. How much work I did first time, how much time I spent second time. I actually used 5. I was so lazy, I didn't even change A and B. A lazy program is always a good program. Do the least amount of calculations you can, but this is not that. We should change A and B. This should be 4. But luckily it's okay, right? Because it doesn't matter. This just makes the interval bigger. Anyway, so I actually didn't change the algorithm at all because the algorithm is the same. So that's how you want to write your algorithms. You've done that for backward, forward, and other things. Back substitution, forward substitution, and other algorithms that we covered. So the only thing that's changed is that I am changing my function here, and I need to update A and B. Happens to be correct for this example too, even though I didn't change it. And it works. Now this time, after 31 iteration, we find the value of the root, okay? So it is nice to see that the same algorithm can be reused. So that's the end of bisection algorithm. We have a question in chat. Will delta always be equal to 1e negative 9? Yes and no. No, because you can change it. That's your numerical resolution accuracy. I could use something else. I could change it to (1e minus 5). Then it will the algorithm should converge faster because it depends how far you want to go, how close you want to get to actual 0. At some point, you hit the resolution that your program can manage. If you're using a single number, you can carry 8 digits if you, in old computers. If you're carrying a double, it's 16. I think now it's 32 or 64, whatever, right? So then you're limited by that as your maximum resolution. But I'm saying that delta is 1e negative 9, so the final value of the function is less than that. And that's supposedly good enough for us in this case. So now if you're dealing with a problem that has some physical meaning, the threshold has a meaning, right? Maybe you're designing something that the length is in meters, right? Then you say, okay, 1 millimeter is not, its error is fine. My threshold is then 1e negative 3, right? If you're working on nano design, then that's horrible. That's you probably want to do better. So be careful if it's a physical quantity, but just the math example. It can be anything. Does that answer your question, Emerald? Great. So if there's no question, we can move on to Newton's algorithm. Okay, now it gets a little more interesting because we are actually going to rely on a new notion, namely the function must be differentiable, which is a notion in calculus. So Newton's method is also a root finding method. It is successively approximate a root better and better. However, just like bisection method, it is a local search. You need to start somewhere, and there is no guarantee necessarily for this algorithm to find it. Now, for the bisection method, you will find it eventually, because by the theorem, there should be at least one. But Newton method is sensitive to your initial guess. So the idea is that start with an initial guess, reasonably close to the root, then approximately make your guess better and better each time. So we need a rule to design our algorithm. Now this is the principle behind Newton's algorithm. This cartoon is very good from Wikipedia. So this starts from x1, right? It finds the tangent line to the curve, then finds x2, then finds the tangent line. I wish I could pause this, but it's not possible. So we start from x1, find the function, find the tangent line, and whenever your tangent line crosses the x-axis, right, that's your next guess. So what does it mean? Like, what's the idea behind it that we say that pick a point, find a line that is tangent to my function, see where that line becomes 0, and that's your next guess, and keep doing that. So the idea is that we are approximating our functions at that point as if it's a line. Because if it's a line, is the simplest equation we can get, right? Finding the root of a linear equation with single variable is a piece of cake. We just divide the right-hand side by the left-hand side coefficient, right? Now, is that accurate and correct always? How good this line here describes my function? Not bad. Your answer is also not bad. Yeah, not bad. It couldn't be worse, right? Because it, like here is, right? I mean, there is a region that line is not too bad. Like you can say, I know, they're not the same, but it's approximating it pretty good. When there are sharp curvatures, right? The curvature is higher. Then you pick a point and attach a line to be tangent to the curve. Then it's only valid for a tiny, tiny interval, right? So then it's not a good approximation. Now, do we know how the function changes over the domain? No, because the function can be anything, right? If the function can be anything, then who knows? Maybe it's a good model, maybe it's not. So, depends on a lot of factors, but assuming the line is a good approximation locally, right? Then we can have a succession rule to find the root. Which brings us to the notion of derivative. Now, we could start from this idea that I'm going to replace my function with a line at each point, right? And then I find out where that line crosses the x-axis. That's my new point. I find the value of the function, and I find a new line, and I keep doing that until I find the root, because at some point, these successive approximation hopefully will lead to the solution. Then you might ask, how do you find the line? What's the definition of line attached to a point for a curve, for function? This is where the notion of derivative comes in. To find that line, I need to know the slope. The slope is basically something you can motivate physically for talking about a derivative. The derivative of a function is an analytical way to exactly find that slope. Via a tool in calculus is called differentiation. So that's why we say a function must be differentiable. So that means that it exists. And so we have a question. Does this fall apart if f of x for some x value is some local max or min? Very good question. Now, you're using your knowledge that you know that at local max or min, the derivative is 0. Then we will see in the algorithm that what we do with that case, right? But if somebody has absolutely no clue about calculus, right, you would never ask that. Because in calculus, you learn that the maximum and minimum of points of the function, derivative should be 0. That's a necessary condition. We touch on this idea inside the algorithm. So I'm going to assume people don't know calculus, right? So I don't talk about that necessary condition and stuff. Okay, so I have this curve, and I want to find a tangent line. How do I do that? I don't know how to take derivative. So somebody with more advanced knowledge is telling me take the derivative of your function, but I don't know how to do that. Imagine me, I'm just an absolute clueless guy about calculus. Talk about slope, right? Let's say we live in, when Jesse might remember that, when derivative was invented, was it 17th century? Let's say we live in 16th century and we want to solve this problem. Now, what is the slope here? If I move my x-axis here, right? How do you define the slope? Let's say we know a little trick, right? The tangent. The tangent of this angle is basically our slope, which we know is delta of function over delta of x. So the rate this function is rising over the rate you're running over the x-axis, this is the slope. Indeed, this is the approximation of, let's say, pick two values. This is an approximation of something you will learn as derivative. That's an analytical tool. You take the limit, you make this delta to go to 0, and then you find out an exact model for that. So this is good enough for us. We have the notion of slope, and I know that the equation of a line is something like this, m times x plus b. Now from here, you can say that I know one single point, right? What's the value of my line? And that's the point I want to define the line, right? So f of, let's say, x1 equals m x1 plus b. So you find b is f of x1 minus m times x1. So we substitute back here. Y equals m x plus f of x1 minus m x1. This will give us m times x minus x1 plus f of x1. Right? This is what I'm talking about up there. Now, m is the slope. You see the derivative here, but you can think about it as delta f times delta x. So we can actually do this with no knowledge of calculus using notion of delta. Okay, so I can actually define exactly a line at arbitrary point on the curve by knowing its slope and the point that I have already. Okay, so now what the next question is, how do you actually calculate this delta? We're looking for ideas of how do you define this delta f over delta x. In particular, what are x1 and x2? Sounds like I have so many options. And that brings us to the notion of finite difference method. So the finite difference method is a way of approximating the derivative, the slope, when you can only evaluate your function. You do not know anything else. There are three ways for calculating the finite difference. The first one is forward difference. The forward difference is it's saying that the derivative of this function at the point A can be approximated as f of x plus sum h minus f of x divided by h. You could think about h as delta x, some small movement. So shift x a little bit forward, right? You see in the picture this delta. From x, wherever you are, you want to get the line, move a delta forward. Evaluate your function, right? Now you have 2 points. These 2 points should give you the line, and the slope is given to you by this forward difference. This is a terrible line. Okay, so, well, that's just one idea. Another idea is the backward difference. This was a fun time when people could invent little things. So you can say, I like to go backward. And you can do that. There's nothing wrong with that. You can go back, calculate your function. Now you have 2 points, and you get another line. Now, if the function is truly differentiable, these two should roughly give you the same thing. Numerically, if they disagree, then something is wrong. The function is not probably differentiable at that point. Because although the lines are very different, they are going through the same point, right? Now, this picture is super exaggerated. The delta is so huge. What you choose for h is so tiny that these lines are a little, right? Variation, you should be able to approximate the line, right? It's not, this picture is, again, exaggerated. The delta we choose is very, very small. You can imagine a single hair, that thickness. Now, a better idea is I think I have I think this might be correct. Double check, but I think first I wrote it wrong for the backward. So, but the idea is forward, move a delta forward, take the delta, right? Backward difference is move a delta backward and then take the difference. A better idea is central difference, do both of them at the same time. Move forward, look forward and watch your back at the same time, right? It gives you a delta forward and backward, divide by 2h, because now we are taking 2 h steps. This tends to be better. It is a better approximation, but as you can see, for forward and backward, you only need to evaluate a new function once, right? For central, you have to do it twice. Maybe this is not a problem, but maybe sometimes evaluating the function, that could be the most expensive part of your algorithm in general when you generalize this to higher dimensions. But for now, this is not a problem, and this is a better approximation. This is what we're going to use. So we have replaced the derivative with this idea of central or symmetric finite difference. The first time I saw finite difference was my undergrad, I think 3rd year. Toward 4th year, I had a heat transfer course. It's a crazy course, mechanical equations for thermodynamics, heat transfer, convection. And then there was a partial differential equation, then the teacher started, let me teach you finite difference to help to solve this. It was a very late stage of my undergrad. So it is very useful to solving plenty of problems in engineering. Which, by the way, you can call this idea of approximating the continuous derivative with this notion of slope and delta a discretization. We're making something continuous to be discrete at certain resolution. So let's go back to the Newton algorithm. Find a line at the arbitrary point that we are, xn. To find the root of f, because we approximate our function with that line, set the line equation to be 0. So set y to be 0. Besides, replace the derivative with the central difference, find a difference we just talked about. This gives you an equation. From here, you can solve for x, which will be xn minus 2h times f of xn divided by f of xn plus h minus f of xn minus h, right? It's a simple equation, some manipulation, and then you find x as a function of where you are, xn. And then you can call this xn plus 1. Okay, so my next step is where I am plus some delta movement. This notion of delta movement, this one idea is this Newton's method, and that's about approximating your function with a line, right? Which in general, in Newton algorithm, it will be right? You will have the derivative, but we don't know what to do with the derivative. We replace it with a idea of central finite difference. So we get a more specialized version of Newton's algorithm, and then we call this whole thing delta. So there could be forward version, there could be backward version, right? With finite difference, maybe you do the derivative exactly, your choice. All of them are Newton's algorithm. Newton algorithm doesn't specify how to calculate the derivative. It is just telling you approximate your function and then find this succession rule. And that's basically the idea. So we find x. Now we have a succession rule. Where do we start? We start with an initial guess. Pick a guess where you are, and then iterate. So now we need to turn this into an algorithm. So one important fact is that h must be small. Do not pick h that is like 1 or 0.5. It's supposed to be a tiny value. Do you have a question? No? So we got our Rob 101 algorithm. This was not a thing outside of Rob 101. You learn Newton, you learn finite difference. We successfully combined them. Congratulations. This is our own, very own algorithm. So let's solve the same problem. Let's see what I am implementing here. So like before, I'm implementing my function. My initial guess, so unlike the bisection method when we had A and B, right? I don't need an interval here. I just need an initial guess. And this h value, you can just set a small default value. You don't need to necessarily change it. We could just set h to be 1e negative 3 or 4 or 5, whatever, right? Should be good enough in general. Although tunable, as long as it's small, it should be fine in general. I leave the delta same for convergence. I need a max iteration. I need a counter because I want to know how many iterations it takes for the algorithm to converge. So the first step, what I do, I evaluate the slope. Given that I know I am at x0 right now, I'm evaluating each of these terms, right? F of x0 minus h, f of x0 itself, f of x0 plus h, my delta f, right? Which is a difference based on the naming that I use, is f2 minus f0. Then check if the delta is, if the absolute value of delta of your function, right, is very small, we're in trouble because of that advanced fact that Luke brought up, that derivative is 0, we can't move. It's become flat, right? We're at a flat point, we cannot move. So then it's not going to converge. So we break the algorithm. Sadly, we have to end the search. Again, if that's not a problem, calculate the delta x. I call it dx, which is negative of 2 times h divided by times f1 divided by f2 minus f0. My function is central delta, right? Now, if delta x is 0, then I'm converged because my next point will be almost the same point I am, right? If the delta is 0, that means I'm not going to move much. So there's no point in taking in a step. It is converged. So that's good news. If delta is 0, that's good. Otherwise, which is most of the time, your new point, which I could write x0 plus equal dx, right? My new point is wherever I am plus delta. Now, I am using the same x0. You don't have to use your initial guess. Probably it's better not to do that. Took 6 iterations. What's the difference? Previously, it was how many? 33? 33 iterations. Newton's algorithm is converging in 6 iterations. That's a huge difference. So it turns out that idea of calculus and linear approximation of function is not so bad. It is converging much faster. Now, there are 2 ideas for basically efficiency of your algorithm. If you're a computer scientist, you might want to time it. Say, my algorithm scales like this, and it takes less time. If you're a mathematician, you might want to count the number of iterations. For a mathematician, this is much faster, even though at every iteration, you might do more calculations, right? Will you come time-wise on top, doing more expensive calculations and doing less iterations? Maybe, I don't know. You need to look into a particular problem. But we're definitely morally on top because we're doing 6 iterations as opposed to 33 with the idea of slope. That's really exciting. Same function again. This is the code to plot it. 5 iterations. So I don't think it was by chance, right? 2 different examples, 30 plus iterations came down to 5, 6. And in fact, if you look at the function value, this is so much smaller as well. This is several order of magnitude smaller than the previous function. It's very close to the actual root. So Newton algorithm is still one of the best root finding algorithms that we have in numerical analysis. We use its optimization version later for vector valued functions. Now there's no need going over the code. The code is the same. I just changed the function. Now, one remark, that in a course, maybe something that is called numerical analysis or something that they want to drive bounds and prove convergence for algorithms, you will see that bisection has a linear convergence rate. So the rate of convergence, right, increases linearly with the number of iterations. Newton has a quadratic relationship. That means you could think about that your number of iterations should be square root of whatever is bisection. So as you scale it, the difference between linear and quadratic is huge if you increase